Assalamu alaikum warahmatullahi wabarakatuh.
Welcome to the Deep Dive. Today, we're not just dreaming about personal flight. We're really digging into the nuts and bolts of building it yourself. Specifically, this idea, this ambition of creating your own personal high-performance aircraft. You know, the kind that makes your neighbors think, wait, did they just build a fighter jet in their garage? But let's be clear right off the bat. We need to set the scope here. We're not talking about, illegally cobbling together an F-35 from scrap parts. That's fantasy. We're talking about building a legal, achievable, well, let's call it a fighter-like experimental jet aircraft, or maybe a high-G aerobatic plane, all through licensed amateur kit programs. It's a really crucial distinction, isn't it, between some high-stakes dream and a serious, maybe 4-year FAA-compliant engineering project.
Absolutely. And compliance, well, that's the bedrock. The absolute gatekeeper for this whole home-built world, whether it's a simple piston plane or a mini jet, is the FAA's 51% rule. It's critical. Basically, you, the builder, have to prove, and I mean prove with paperwork, that you did more than half the construction work yourself. And there's a good reason for that rule. It forces you to get intimate with every single part, every rivet, every spar, every load path. It ensures the person actually flying this experimental machine really understands how it holds together. Honestly, that documentation trail, that's often the first big hurdle people run into.
Right, that 51% proof, that's your actual ticket to fly it legally. So, our mission today, we want to give you a bit of a roadmap, analyze 3 possible paths you could take. Path 1, the pure jet experience. Path 2, the high-G stunt plane. And Path 3, the really ambitious electric or maybe even jetpack challenge. We'll look at cost, time, and importantly, the physics that just won't budge. Okay, let's jump right into the really exciting option first, the path of power. For that genuine personal jet feeling, the most established practical way right now seems to be this Sonex, Subsonics, JSX2 kit. This thing is pretty much the state-of-the-art for amateur jet builders. It gets you real jet capability outside of, military or big commercial stuff.
Yeah, it's quite something. What's really striking is how much performance they squeeze out of such a minimal design. I mean, the empty weight is tiny, maybe 650 to 750 pounds. But it cruises impressively fast, like 230, 240 miles per hour, gives you that genuine fighter-like feel. And the construction, they use simplified methods, aircraft-grade aluminum, fiberglass nose cone. It all helps the builder actually meet that tough 51% rule.
Okay, let's talk money, because this is where, the dream meets reality pretty hard. Total project cost, everything included, kit, avionics, paint, the works, you're easily looking at $200,000, maybe $250,000 plus. But here's the part that really jumped out at me from the sources. The airframe kit, just the structure, is about $135,000. Hang on, if the airframe itself, fuselage, wings, controls is $135K, and you mentioned the single most expensive piece, that turbine engine, costs around $65,000 alone.
That's right.
That engine is nearly half the cost of the entire airframe. Why is it so expensive? Just the miniaturization.
Well, yeah, that's where the really specialized engineering comes in. You're not buying some off-the-shelf engine like in a Cessna. You're buying a highly tuned, very specific, single-stage turbine. It's the little marvel, thermodynamically speaking, designed to be incredibly light, but still push out, 240 pounds of thrust? That combination, tiny size, precision engineering, and frankly, very low production numbers, it just always makes that turbine disproportionately expensive compared to the metal bits of the airframe. And the cost doesn't stop when you buy it. Building it takes time, sure, maybe 1,200 to 1,500 hours. That's a year, maybe 3 years of your life. But then you gotta fly the thing. The operating costs, pretty staggering. You're burning jet fuel at about 30 gallons an hour, depending on fuel prices. That's easily $200 to $300 per flight hour, just for fuel.
Wow. Okay, so let's say you've got the money, you've put in the thousands of hours, and you're already a licensed pilot. Can you just hop in and go?
Oh, definitely not. The regulatory side for these experimental jets is stricter than for piston planes. You absolutely have to get a specific letter of authorization and LOA from the FAA. Because it's amateur built, it's unique. The FAA needs proof you know how to handle that specific type of aircraft before you fly solo. It reflects the inherently higher risk. And then after the build, you face the real test, a detailed FAA inspection, followed by a mandatory flight test phase, 25 to 40 hours of rigorous flying. And these flights have to be over unpopulated areas. It's all about proving the design is safe and airworthy before they finally give you that certificate. It's a serious multi-step process.
Okay, so that's the jet path, defined by speed, cutting-edge tech, but also immense cost, both upfront and ongoing. Let's pivot now, a completely different approach, focusing on structural strength and pure maneuverability. We're talking about building an aerobatic stunt plane. If pulling G's is your main goal, This seems like the most structurally sound and maybe more financially realistic route.
It's a total shift in engineering focus, isn't it? You're not building for top speed anymore. You're building to withstand high G loads. Competition aerobatic planes like the classic Pitt Special, they're typically stressed for +6 Gs and -3 Gs. That's standard, and you need that toughness. Pulling a really tight, clean competition loop, that requires hitting 6 Gs to keep the shape perfect.
And the icon in this world, the go-to classic, is the Pitt Special series. This path is way more accessible financially than the jet. You might be looking at, what, $30,000 to $50,000 if you scratch build with a modest engine? Maybe for $75,000 fully kitted out for competition? That's the level of investment a dedicated hobbyist can actually wrap their head around, you know?
And the build time is also more manageable generally. Still a huge effort, don't get me wrong, anywhere from 1,000 to maybe 4,000 hours. But it's very doable over 1 to 3 years, especially with the really good kits available now. It feels like a more, well, structured project.
But it's not just about being strong, right? It's about flying upside down. That needs some specific design features. What does a builder need to know about, like the wing shape for inverted flight?
Ah, yes, this is crucial. This gets into the aerodynamics. Unlike your typical plane wing, which is curved more on top for lift when upright, aerobatic planes must have symmetrical airfoils. That means the curve is exactly the same on the top and the bottom of the wing. Why? Simple. They need to produce lift just as well, whether you're right side up or completely upside down. Essential for sustained inverted flight or complex stuff like outside loops.
And when you're upside down, gravity is suddenly working against the engine's normal operation. What happens if you skip those special systems you need?
Well, you lose power. Fast. Potentially disastrously fast. If you try to fly inverted for any length of time without special aerobatic carburetors or fuel injection, gravity just pulls the fuel away from where the engine needs it. Fuel starvation. Bang. Same goes for the oil system. You need special tanks, inverted pickups, pumps, basically a whole system designed to keep everything luculated, even when the engine's oil pan is pointing at the sky. It's designed to work through 360 degrees.
I find the construction materials comparison really interesting too. The sources lay out two traditional but very different ways to build these. You've got the sort of romantic approach, Sitka spruce and plywood, old school wood.
Yeah.
It's relatively cheap, you can repair it easily, and the strength to weight is fantastic. But then there's the other way. The heavy-duty cage made of 4130 chromoly steel tubing offers much better crash protection. It's super durable, but it's heavier. And importantly, you need to be good at welding, TIG, or MIG. It's kind of a choice between lightweight tradition and rugged safety.
And no matter how you build it, wood or steel, there's one piece of safety gear that's non-negotiable if you're doing aerobatics. A personal parachute. Costs maybe $1,500 to $3,000. It's absolutely essential. You just can't safely push the envelope, stressing the aircraft to its limits, without that last line of defense.
Okay, we've covered the established tech jets and props. Now let's look at the cutting edge, the modern ambition, electric aircraft, and yes, the personal jetpack. This feels like the segment where brilliant engineering ideas run smack into a hard wall of physics.
Oh, they really do. And this is the critical issue for the future of personal flight, I think. The absolute fundamental constraint is battery energy density. If you actually compare how much energy you can store per kilogram, the difference between fuel and batteries is, well, it's staggering. Jet A fuel, your basic chemical energy, packs an incredible punch, roughly 12,000 watt-hours per kilogram. Now, current lithium-ion batteries, the best ones you can realistically get today at the pack level with all the safety systems, maybe 250 to 300 watt-hours per kilogram.
Whoa, hold on. Let me process that. 12,000 versus maybe 300. That's a 40 to 50 times disadvantage for batteries. So, to carry the same flight energy, the battery has to weigh 40 times more than the fuel. Why is the gap that enormous?
It boils down to the difference between releasing chemical energy through combustion versus storing and releasing electrical energy electrochemically. Burning fuel is direct mass-to-energy conversion, pretty much. A battery pack, though. It's a whole device. You've got the active materials, yes, lithium, carbon, whatever, but you also have the heavy casing, the cooling systems, fire suppression, all the battery management electronics. A huge chunk of the battery's weight is just structure and support. Inert mass, that's what fuels your energy density compared to simple fuel.
And you see the direct, almost brutal consequence of this when you look at the dream of the personal electric jetpack. A working jetpack needs a lot of continuous power, maybe 15 to 50 kilowatts, just to stay airborne and maneuver. But because batteries are so heavy for the energy they hold, well, the battery pack you'd need for even a short, useful flight, say, just 15 minutes would weigh something like 60 to 100 kilograms.
That's 130 to 220 pounds.
Exactly. That battery weight alone makes the whole thing barely usable, frankly, unless you weigh next to nothing yourself. It's like strapping a washing machine to your back for a 10-minute hop. Impractical.
Which is why, realistically, the practical electric path has to start much smaller. The best entry point right now. Build an RC electric stunt plane. Seriously, for maybe $200, $400 total, you learn so much. Control dynamics, how to match motors and props, understanding that crucial, say, 1.5 to 1 thrust-to-weight ratio you need for real aerobatics.
And even scaling that up to a full-size electric plane. Let's imagine a 400 or 500 kilogram electric aerobatic plane. You put in modern, efficient 50, 75 kilowatt motors, the endurance is still cripplingly short. You're talking maybe 20, 30 minutes of just cruising around. Or like 10, 15 minutes of actual hard aerobatics. You spend way more time charging it than flying it.
Yeah, the industry conclusion here is pretty sobering, honestly. Practical, useful, long-range electric flight, the kind that gets you, say, 500 kilometers, like a decent car trip that's just not here today. Most projections put that kind of capability somewhere between 2035 and 2040. And that entire timeline depends on next-gen power sources, probably solid-state batteries, actually maturing and becoming commercially viable. Today's lithium-ion tech just doesn't cut it for serious flight utility. So let's try to wrap these three paths up for you. First, we looked at the jet, the subsonics. Amazing speed, very cool, but high cost to buy, high cost to run. Second, the aerobatic plane, like the Pitts. Proven design, durable, handles high Gs, and it's the most financially and structurally achievable route for a dedicated builder. And third, the electric path. Huge feature promise, obviously, but right now, it's fundamentally blocked by that massive 40 times energy density gap in batteries, severely limiting how long and how far you can fly.
So, assuming you've got the mechanical skills, you can read blueprints, you're okay with riveting or welding complex projects, the most sensible way to start seems pretty clear. You really need to nail the flight dynamics and the building techniques before you invest in a full-size aircraft, which points towards starting with RC aerobatic models. Spend maybe the first 6 months mastering those, get the reflexes, understand motor matching before you're sitting in something costing $75,000 or more once you've got that foundation. Then you commit to a full-scale Pitts kit or something similar. And that's a serious commitment, 2 to 4 years, 1,500 hours plus, but it leads to an actual plane you can fly.
And critically, don't try to do it in a vacuum. Get involved immediately with the Experimental Aircraft Association, EAA. They are the resource. Mentorship, help finding tools, inspection advice, navigating all that 51% rule paperwork. They're the community that helps get these projects off the ground, literally.
And please, heed this last dose of reality. Time management. These multi-year builds, they have a nasty habit of taking longer than you think. Much longer. You have to account for builder burnout, parts delays, unexpected problems, regulatory hurdles. Our sources consistently say projects take 50 to 100% longer than the initial optimistic estimate. If you think 3 years, honestly, budget for 5. Which brings us to our final thoughts, something for you to chew on as you maybe start sketching your dream plane on a napkin. If we accept that the airframe technology, the wood, the metal, the composites, it's pretty much there, it's accessible, it's proven, then the single biggest roadblock to truly revolutionizing personal flight is the power source. We could build amazing airframes today. So if today's chemical battery seems stuck around that limiting 250, 300 watt-hours per kilogram mark, what's next? What emerging, maybe non-chemical technology, perhaps a breakthrough in efficient hydrogen fuel cells, or some completely new way to store energy we haven't even thought of yet? What's going to give us that 40 times leap? The leap needed to make long-range electric planes and useful electric jetpacks actually real within our lifetimes. It feels like a chemistry problem now more than an airframe problem. Something to think about. Dive deep, and good luck if you decide to build.